Okay, so part 2 of this video is going to be to prove identities numerically, graphically, and algebraically with the knowledge of what these 6 trig ratios actually equal. And down at the bottom, again, I've identified them as reciprocal identities. They're reciprocal identities because they are true for all values of the variable. So we once again know the tangent is the reciprocal of the cotangent, being the sine over the cos. The cotangent is the reciprocal of the tangent, cos over the sine. The cosecant and the sine are reciprocals of one another, and the secant and the cosine, all right, are actually reciprocals of one another. By definition, these are identities because they're true for all values of the variable. Okay, now our job is going to be to work with more complicated identities. Okay, so we have what has been texted out here as complicated combinations of those 6 trig functions. And what we want to be able to do is we want to be able to say equation or identity. All right, true for only certain values of the variable, or are they true for all values of the variable? And we wanted to be able to do that numerically, algebraically, and also graphically. Okay, so with that in mind, let's take out a sheet of paper, and what I'm going to do is I'm going to break it down into 3 sections. We're going to start first of all with the numerically. Okay, then we're going to endeavor to solve graphically, and then last but not least, we're going to look at a more algebraic approach. So what is it going to mean if I want to prove that the sine of t plus the cos of t times the cotangent of t, all right, is equal to the cosecant of t? So clearly, in this identity, we have a left side and a right side, which we want to prove are equal for all values of t. Numerically, the suggestion is that I should be able to substitute a value for t, and from that I should be able to prove that the left-hand side equals the right-hand side, right? So for example, let's let t equal pi halves. Then on the left side I would have the sine of pi halves plus the cos of pi halves times the cotangent of pi halves. And what would that equal? On the right side, I will have the cosecant of pi halves. So what I'm saying is, numerically, can I substitute a value for the variable, any value for the variable, and end up having it equal, or have it be true? Okay, the sine of pi halves I know is 1. The cos of pi halves is 0. The cotangent of pi halves would be the cos of pi halves, which is 0, over the sine of pi halves, which is 1, and that too would be 0. So I have 1 plus 0, which is 1. The cosecant of pi halves is 1 over the sine of pi halves. We know that the sine of pi halves is 1, and the reciprocal of 1 is 1. So numerically, I've been able to prove that the left side is indeed equal to the right side. Now, it doesn't take long for me to understand that this is going to be an incredibly limiting strategy. All right, because the question is, how could I possibly test all values of t? I can't. All right, we know that when it comes to these trig ratios, the domain of the functions is the real numbers. There's no way that I could substitute all the real numbers in for t in order to verify that the left side of this identity is always equal to the right side of the identity for all values of the variable. The question is, I can't test all values of the variable. Okay, so clearly that strategy has limits. So what could I do to solve this over the real numbers. Okay, so another possible strategy is, can I do it graphically? Can I actually prove that the sine of t plus the cos of t times the cotangent of t, okay, and I'm just going to leave a little spot there, is actually equal to the cosecant of t? I mean, is that true for all values of the variable? The suggestion is that I should be able to graph the left side of the equation. I should be able to graph the right side of the equation, and do the two graphs actually end up being the same thing? Okay, so if I take out my calculator, let's see what we can do with that. Okay. Now, the first thing I think I'm going to have to do is I'm going to have to set my Windows settings for this. Okay. Typically, I know that the sine and the cos have a range of -1 to 1. I know that I'm playing around with that a little bit, so I'm going to actually take my y min as set it to -5, and I'm going to set my y max to +5. Can you see that all right? Okay. And I know that because I'm in radians, I probably want to set up my domain in terms of radians as well. And typically I've gone from 2 pi, all right, to -2 pi. And I think this time I'm going to go from 6 pi, all right, -6 pi to +6 pi, and I'm going to go up by pi quarters. I'm just going to give myself some real freedom on the domain, all right, to extend this graph, perhaps graph more than 1 or 2 periods at a time. Okay, so now I'm going to go to y equals. I have a plot on there that I'm going to turn off, and I'm going to put in the left side of this equation, all right, which sits right there. I'm going to define my first value of y as the sine of, I've got no x when I'm working in function, or sorry, no t when I'm working in function mode, so I'm going to replace that with x. So I'm just going to let x equal t here, all right, when I go to graph it. So I've got the sine of x, and then what I want is the cos of x times the cotangent. I've got two options here, all right. I could actually write that as the cos over the sine, or maybe I could just write it as 1 divided by the tangent of x, like so. Okay. Now, interestingly enough, when I hit graph, something kind of cool happens. Okay, and I look at it and I go, this is not a surprise to me. All right, because I have graphed the tangent and the cotangent in the past, the idea that I suddenly have some asymptotes showing up indicates to me that there must be some restrictions on this particular variable. There's going to be some values of t for which this just isn't going to work. Okay, and we're going to address those restrictions here in a moment. But in the meantime, let's go and do the following. Remember that we wanted that to equal the right side, which is the cosecant of t, or 1 over the sine of t. So I'm going to set y2 to 1 over the sine of x, my substituted variable. And what I'm going to do, I'm going to go over here to my first one, and I'm going to actually turn it off. When I highlight my equals and I hit enter, you'll notice that, all right, the equals is not highlighted any longer. All right, so the only active graph right now is y2. Okay, so let's take a look at y2. And the moment I do that, I can see, oh, yeah, you know what? That looks an awful lot like the first graph that I had, right? In fact, if I go to y equals and I reactivate that equation and I hit graph, all right, what you're going to see is that the graph just sits there. Okay, those two equations are identical. It's not like one graph is superimposed on the other. So graphically, I can actually prove that these two sides of the equation, the left side and the right side, are indeed equal. Now, let's do the following, because we did want to graph it, and I don't want to graph that many asymptotes. So how about we go back to our window setting, and we go from, say, -pi, all right, to +pi. Is that enough to see a period? Okay. Yeah, that's a little nicer. Okay. Okay. So there's one really nice period. Now the question would be, where are those asymptotes? Well, asymptotes, again, come from where there are restrictions on the variable. In other words, there are going to be places for which this particular left side and right side of this identity are not going to be defined. You'll recall that if I rewrite this identity using nothing but, there we go, sines and cosines, so there's the left side, and the right side looks like this. I know that when I've dealt with rational expressions in the past, I know I can't divide by 0. And so that occurs when the denominator is 0. So because I can't divide by 0, that means that the sine of t cannot be 0. And where is the sine 0? Well, the sine is actually 0, all right, at all multiples of pi. 0, pi, 2 pi, 3 pi, and so on. All multiples of pi where k is an element of the integers. So I have some definite restrictions on the variable that result in asymptotes. So if I were to sketch this like so, and you recall that I went from negative pi to pi, okay, so I'm just going to go 1, 2, 3, there's negative pi, and 1, 2, 3, 4, there's positive pi, because remember I was going up by pi quarters, right? Okay, I have an asymptote here. I have an asymptote at the y-axis, and I have an asymptote here. All right, now remember I'm providing a sketch. I'm looking at my graph and I'm pretty sure that at pi halves here, all right, I have 1. Oh, yeah, I should be good with that because at pi halves you can see it right here in this, all right, numeric example that I'm at 1. So pi halves I'm at -1 and +1. So I actually have a graph that looks something like this. And I know that both the sine of t and the cos of t times the cotangent of t and the cosecant of t look identical to this graph. Okay? My TI-83 has, all right, confirmed that. Of course, knowing that I do have restrictions on that particular variable because the denominator can't be 0. Okay, let's talk a little bit about the two solutions that we have so far, because they both have limitations. We said numerically that has limitations because there's no way to test for all members of the domain. Not going to happen, and that is an identity, right? By definition, identity has to be true for all values of the variable. How am I going to test them all? Problem. The graphical solution definitely shows me that for all values of the variable, not including where the side is 0, for all values of the variable, I do in fact have equality of the left side and the right-hand side. The restriction, or the limitation rather, of the graphical model is that, well, do I always have a calculator? Will I always have a calculator? I know that on the exam, for 2 hours of it, I won't. So how am I going to prove something is true, left side, that is, sorry, an equation is true, left side equals right-hand side for all values of the variable, making it an identity without a calculator? And so that brings up our third strategy, which is one that's algebraic. Okay? Now, if I'm going to prove something is algebraic, I think that it probably makes some sense, all right, to talk about a few other identities that we all said we were already familiar with, because we recall down here that we also have a Pythagorean identity that we identified back in the first part of this video. We've got Waldo here, for which we know the cos squared of an angle plus the sine squared of an angle is equal to 1. And there are certainly variations of Waldo that we have used in our first unit to be able to solve, for example, the cos when I know the sine, or the sine when I know the cos. So we're going to elaborate on some variations of the Pythagorean identity in future videos. But for now, I just want to draw your attention to what is a known identity. What are known identities? Because those known identities are going to help us, all right, prove future identities. Okay, so once you have proved that something's true for all values of the variable, it becomes an identity, and it's something that can be used going forward. Now, when I'm solving things algebraically, in your notes, you will find what is called an identity strategy wheel. And this strategy wheel, in my mind, is golden. It's something that you should keep in front of you all the time, because it has been my experience that this set of strategies or procedures will always allow you to solve for any identity algebraically. Okay? Within the strategy, like where there are these little arrows, you may find yourself simplifying as you go from one strategy to the next. But the strategies themselves are golden, because they will always get you, all right, to your destination. Now, my job is also to show you where there are shortcuts, okay? But this strategy wheel works, and I'm going to actually use it now. I'm going to actually use the strategy wheel to prove that past identity. That would be, I want to prove that the sine of t plus the cos of t times the cotangent of t is equal to the cosecant of t. There's the question mark. Now remember, what we're trying to do is we're trying to prove the left side of the identity equals the right side of the identity. Usually when you're proving identities, it's best to start with the most complicated side. Okay? Following the strategy wheel, you will notice that what you want to do is you want to prove that the left side and the right side are equal, and it probably works best, all right, to work with the most complicated side. Remember again that your job is to prove that the equals belongs there for all values of the variable. Okay, so what I typically do is I typically work with one side of the identity and I try to produce the other side. This is extremely important. I cannot write the equals in until the identity has been established. We're going to use today the strategy wheel to actually prove this particular identity. Now, given the fact that it is already in your notes, you don't have to copy this down. Maybe just listen, and I should be able to identify at each step what it is I did, all right, to that particular equation. Remember, my job is to prove the left side equals the right side. My brain works this way. I want to take the complex and make it simpler. Very rarely do I want to take the simpler and make it more complicated. So I'm going to start with the left side of the equation, and I'm going to hope that eventually I can produce the right side by using algebraic means. Now, if I'm looking at the strategy wheel suggests that the first thing that I should do if I want to prove this identity is convert everything to sines and cosines. Okay, easily enough done. I did it before, all right here in this step, so I'm going to do it again. The sine of t plus the cos of t times the cotangent of t, which is the cos of t over the sine of t. Like so. Okay? So remember what this is. This is step 1 in the strategy wheel. Step 1, convert to sines and cosines. Okay, and I'm not going to use theta there just because I have t there. I'm going to change that to t and be consistent with my variable. Okay, remember I said that before we activate this next strategy, which is to put over a common denominator, you may want to simplify it first. Okay, so I can do that right here. If I were to take that product, which occurs in this second term, I'm going to get the cos squared of t all over the sine of t, like so. Okay, Now I'm thinking I can go to step 2, because step number 2 in my strategy wheel says put over a common denominator. That, of course, happens when I'm asked to add fractions, which, by the way, I am, and frequently will be asked to do because of those reciprocal identities. So how do I add the sine of t with a denominator of 1 to the cosquared of t with a denominator of the sine of t? Well, I think I need a denominator that is equal to the sine of t. Okay, so in step 2, I'm actually going to put over a common denominator. Okay, if I'm going to change this term to a denominator of the sine of t, then I'm going to have to multiply the sine of t by both the numerator and the denominator, which, by the way, is a special form of 1. Okay, and that is going to give me the sine squared over the sine of t plus the cos squared over the sine of t. Okay, step 2, putting over a common denominator is done. Okay, let's move to step 3. Step 3 says, okay, can you substitute with another identity? Certainly can, because I identify that my numerator is Waldo. Okay, and so substituting with an identity allows me to replace the sine squared plus the cos squared, all right, with 1. So now I get 1 over the sine of t. Now remember that when I'm proving an identity, my whole goal is that I start and I have a destination. Okay, it's kind of like a road trip. Okay, you've got a beginning point, you have a destination. There are going to be lots of ways to that destination possibly. Okay, but it's the idea that you always want to keep your destination in mind. And on the right hand side, I have the cosecant of t. So my goal was to take the left side and make it look like this. I want to produce this using those steps. And I've just done it, because what is 1 over the sine? It's the cosecant, and that would be the right hand side. So I've managed to prove that the left side is equal to the right side, and I've done it with the conversion of sines to cosines, putting over common denominator, replacing with an identity. Okay, I know the equals belongs now, and that identity is true for all values of the variable.